Daren May. You can find me on Twitter at Daren May. I have a company, CustomMayd. You can look that up. The link at the bottom, that's where the source code in this presentation sits on GitHub. So you can go and see that if you're interested. So, Windows 10 composition. Really what we're talking about here is the new visual layer that's part of Windows 10. And you might ask yourself, well, what is a visual layer? Well, in this instance, what it is it's a retained mode graphics API that leverages the graphics hardware of your system to produce very smooth animations and effects leveraging your graphics card. So I just mentioned retained mode, and there's two types of graphics APIs that are available, really. A retained mode and an immediate mode. The idea of retained mode is your application defines a scene and hands it over to the API, and the API maintains a model of that scene in memory, so you don't have to keep redrawing it from your API perspective. You just have to send changes over to the API. Immediate mode means your application is responsible every single frame for specifying exactly what's rendered on there. So you could imagine if you're building a UWP application, that would be a lot of work to keep redefining your UI every time. So we use retained mode. Just out of interest, how many people here have Windows 10 installed? Oh, somebody at the back there doesn't. Oh, dear. How many people have built a UWP application? OK, so just over 50%. That's a good position to be in. So where does composition sit in this visual layer? Well, the idea is that it lies in between your UI framework, which for UWP is XAML, and your underlying graphics APIs, which is DirectX. So most people are familiar with DirectX. It's what's leveraged to build Windows games and Xbox games and so on, and is a high-performance abstraction that sits above your graphics card. It's typically coded against using C++, which means it's not the easiest to consume, and it's got a very challenging model. It's only recently supported multiple threads for rendering and so on, and it's pretty challenging to use. The idea is Windows UI composition abstracts that API and gives you a much simplified way of leveraging that power. So the idea is that the Windows UI XAML framework leverages that all the time anyway to build out its performance. It takes the output of your controls and passes it through to the graphics card. But we can also directly leverage that capability. And that's what this session is about, is how we can leverage those capabilities of the composition API. My session at 3:20 will be talking about how this capability has been pulled up into the full creators update of Windows 10 and how you can use existing controls to get some of this capability. So what's in the visual layer? Well, we have three major areas. We have content, that which is being displayed. We have effects, manipulations that occur on the content. And we have animations, which is pretty self-evident. So if we look at content, content starts off as a visual. Now, every control or whatever that you render in XAML has what is called a backing visual. And that is the output of the rendering of that particular control. And that then gets passed off to your graphics card to render. Okay? We can also start interacting directly with that visual. We can add child visual to that visual. And one of those is a container visual. That inherits from visual, so basically it's something that can be rendered by the graphics card, but as container kind of implies, it can also contain content. And the type of content it can contain is a sprite visual. So if you've ever used any sort of gaming infrastructure or anything along those lines, you're probably familiar with sprites. Sprites are just bitmaps that can be moved around very quickly by a graphics card. And that's exactly the same thing that we're talking about here. Now, a sprite visual can render content typically using a brush. And a brush is, as the name implies, something that paints content. It can be as simple as a solid color, or it can be as rich as a list view with nested data elements. Okay? So that's the idea. That's the infrastructure behind a content. Effects, as the name implies, is something that post-processes the output of a visual and can apply one or more effects in a chain. So the example I'm showing here on your left is a Gaussian blur. So that is taking the output that's being rendered behind this effect layer and applying a Gaussian blur to it. Saturation, for example, can remove color and so on. And there's 14 supported effects in the current API. These effects are surfaced up through Win2D, which is a NuGet package that simplifies interacting with DirectX. And most of those effects are available to us in composition. Some of them are not, and the reasons that they're not is they're not high enough performance to occur on a frame-by-frame basis. We can also leverage lighting, which is a relatively new concept within these flat 2D UIs. So we can actually start playing around with different types of lighting, such as ambient, spot, and point. You might wonder what the difference between a spotlight and a point light is. Basically, the difference is that a spotlight has an outer cone, which can be a different color than the inner light. So you kind of have two light sources within there. And we'll play around with lighting a little bit in this demo. Animations, that's another very powerful thing. So why do we want to use composition over, say, the XAML animations that are built in? Well, the idea is that we're handing off all of the workload onto our compositor thread, which is part of our operating system. That renders at 60 frames per second and does not load the UI of your application. So your application just hands off the work and your operating system renders it. This means that your animations move in a much smoother fashion. Now, having said that, all of the XAML animations, as long as they're not doing something which manipulates a property that can't be accelerated, are now using the composition animations behind the scenes. So you could go back and leveraging those things. And I'll talk a little bit more about that in my next presentation around the idea of enabling capability and then making it easy. However, we have a number of these types of animations. We have time-based keyframe animations. Most people are familiar with those. You have a starting state, you have an end state, and in the timeline you might have intermediate states. The animation engine then interpolates between those points over a timeline to achieve your end result. You can also apply easing functions which say whether it's a linear interpolation or whether you have a ramp or whatever. Implicit animations build upon that idea, but instead of you manually starting an animation, you instead set up the system to monitor for certain triggering events, for example, the change of an offset, and then the animation will run automatically powered by the system instead of you having to launch it yourself. We'll look at both of those animations in this demo shortly. Expression-based animations are a very neat and cool capability that will monitor one property, then apply an algorithm to it, and take the outcome of that and apply it to another property. An example of that is parallax scrolling, where you have something that moves a large distance in the foreground, but in the background something moves at a much slower rate. And so you use a mathematical function to change those values. We can assign that expression into our animation definition, and the composition system runs that for us automatically. We don't have to worry about it. Input-driven, that can monitor things such as the position of your pointer on the screen, and take that and apply an animation based upon those pointer values. So it can look at property sets, and that kind of ties into expression-based animations as well. The final animation that was introduced as part of Full Creators Update, in fact, is physics-based, where it automatically applies a spring effect to values, so you get bounce, basically. So what we're going to do in this is we're going to look at an application that brings all of these things together, so you get an idea of the power and, to a certain extent, the relative simplicity of leveraging this. So what we've got here is an application. So this is, as I say, the end result. What you have here is you have an image that has a saturation effect applied to it to make it monochromatic. We're then applying an ambient light, which is the purple lighting, which is a little bit difficult to see, but you can see up there in that corner. We then have two point lights that are moving backwards and forwards. One is green, one is yellow. And then what we have sitting on top of this is transparent text that is being composed into the system. It has an animation that's running on it, moving it backwards and forwards. And I'll also show, time allows, a Gaussian blur effect sitting on top of all of these things. So this is what we're going to build. But let's start off with the application. So to illustrate the fact that all of this is happening in composition, this is the only XAML element that we have in our application. It is a root grid. I forgot to turn sleep mode on, so let's put sleep mode on. So all we have is a grid And what we're going to do is we're going to take that backing visual for the grid, which effectively gives us a dimension on the screen, and then we're going to add additional content to that. And all of that's going to be done in code, in the code behind. So if I jump over to the code behind, here's my backing properties. We'll worry about those in a little while. In my constructor, I attach to my loaded event. That's when I'm going to start rendering because my grid has been created. I know the dimensions of my grid at this point in time, so I can start adding content to that grid. Size changed. That's something that we'll also be looking at. Because we're tracking based upon the size of that grid, whenever the size changes on that grid, I want to update perhaps positions of my composition content as well. So that's why I'm attaching to that event. Now let's run this as it stands. And it always takes far too long when you're standing here waiting for builds to actually compile. But what we want to see is the fact that we have a very simple UI at this point. So we have a window, has a black background because I chose the dark theme, and we have this ugly bar across the top. So the first thing we want to do is we want to get rid of that because we want to leverage the whole of our content space. So we have this API, core application, get current view, title bar, extend a view into title bar. Microsoft really did swallow a dictionary when they started creating all of these APIs. So we're going to say true. We want to extend ourselves into our title bar. So if we run that again, what we will see is we extend up to the top of the window, but we still have an ugly block where our buttons sit, he says. But of course, I ran this before, and the transparency is still applying. One thing actually to bear in mind with these is that the metadata associated with your title bar gets stored in the same data area as your previous window position and size. So if you've run your application previously and said extend into the title bar equals true, then you delete that line. It won't assume that you're not extending into the title bar the next time. It remembers that you previously set it to true and will keep applying it. So I forgot about that for the colors. But what you've got here, you'll notice that I'm using, instead of core application, application view. It's one of the annoyances of UWP is there's multiple ways to get at what you believe to be the same object. And these represent different COM interfaces for interacting with APIs. So this is a different title bar, which is the title bar that allows me to change the colors. Okay? So now we have extended our application rendering space up into the title bar area. Now we're going to handle the onloaded event where we're going to start interacting with composition. The first thing we're going to do is we're going to get a reference to the compositor for the current window. So what is the compositor? It is effectively an object factory that gives you access to the composition objects in the context of your current running window. So this is a relatively new API that was introduced to allow you to get to the compositor. You used to have to go through a reference to an element on your current page and ask for the compositor there. This one will always get you the current compositor, which allows you to use it in a lot of different ways. So anyway, the first thing we're going to want to do is we want to load in our background image. We have this new API in Full Creators Update, Load Image Surface. This allows us to start to load an image from a URI. Those of you who are familiar with UWP know that if you have content in your application package, you have to use this MS-AppX protocol to interact with it. So it's stored in assets, and Webster background is the image. This will start an asynchronous load of our image. We actually don't need to wait for that image to complete to be able to carry on with this process. It will load in its own time and render up. You recall I mentioned beforehand that everything is rendered as brushes. So what we have to do is this loads a surface into our graphics card memory with the image in effect as a texture. We then need to create a brush from that surface so we can render it. So we're using our compositor as an object factory to create a surface brush. We're passing in the image surface, and we're specifying that we want our brush to stretch uniform to fill wherever we paint that brush. We then create a sprite visual. You recall me talking about the visual hierarchy, how we have a backing visual for, say, our grid, and we can add to that a container visual, and we can add sprite visuals to container visuals. So what we're doing here is we're creating a sprite visual. We're then saying that the brush of that sprite visual is the background brush we just created from the image. We are then setting its size, because a brush will paint with 0 dimension unless we give it an explicit size. And we're going to say, paint it to the size of our root element, which is the grid that's on our page. Take its render size, and this is an extension method that comes as part of the composition API that converts the size of structure to a vector 2. There are a lot of vectors that are used in composition because that is what underlying APIs leverage. So a vector 2, just 2 properties, an X and a Y. Once we have our background visual, we need to add it to something. So again, we use our compositor to create a container visual. We then add to the children collection of our container visual our background visual, and because this is a background, we say we want to insert it at the bottom. It doesn't actually matter at this point because we have no other children in our collection for our container visual. We could insert it at the top. It's still effectively the only one there. We then use element composition preview, which everyone looks at that and goes, does that mean it's an API that's in preview? No, it doesn't. It's effectively the way to cross the boundaries between visuals and elements. We are going to set the child visual of our root element, which is a grid in XAML, to our container visual. And so if you recall before how we have that hierarchy, we have the backing visual for our grid, we then have a container visual that contains our background brush. So now if I run this up, quick as a flash, what we'll see is the full color image stretched to fill the window. Okay? And that's because our brush is set to track the size. I mentioned the size changed event. If I scroll down quickly to the size changed, what we have down here is, as long as I've defined the background visual, every time I get a size change event on the window, I resize that background visual. So that's why the image retains its dimension as I change this window. Okay? And I did that because nobody wants to see me code all of that. So we have our background image, but it's full color, and I want it to be black and white. So how can I do that? Well, good job you asked. That's the next part of my demo. So what we're going to do is, right now I'm just going to comment out my container visual code, and I'm going to look at adding an effect. And I'm going to leverage the saturation effect to desaturate our image so that it becomes black and white. We're using the Win2D definitions of effects. So one of the interesting things about composition is in most cases, we're not actually really doing anything when we create, say, for example, a saturation effect. What we're really doing is creating a strongly typed property set that defines what the graphics card is going to do down the line. Okay? So I'm creating a definition of a saturation effect, and I said I want saturation to be 0, and I want the source, i.e. the input to this effect, to be something from a composition effect source parameter named background. So this is part of the power of this whole composition system, is we can actually inject values into these effects that get evaluated down the line. So I've created a definition of my saturation effect here. Now I need to create an instance of my effect via the effect factory. So this is using the compositor to create an effect factory using my saturation effect definition. I'm going to create a brush, which is the outcome of that effect, but nothing's actually happened yet. And then I set on my brush a source parameter called background, which matches the definition in the effect, and I pass into that my background brush. So that's how this chain occurs. I take my background, pass it into an effect, the effect gets applied, I take the outcome of that, and I create a background visual with the sprite, and I set the outcome, the saturation brush, as the brush for that visual, set the size of that, again, to my window, and I'm recreating the container here because I disabled it back here. I should comment that out too, since I'm not using that. So I'm recreating background visual here, and then adding everything back into my element composition. So if I run this now, what we should see is the image is now no longer full color. Its saturations have been set to 0, so it's going to be monochromatic. Okay? So that's an example of an effect. Now we want to start getting a little bit more interesting. And for those of you who've had Windows for a long time, you may recall the Zune desktop music player back in the past. What I'm emulating here is one of the now playing effects, just to demonstrate some of the features that people could use if they used the low-level APIs previously. It's now available to us as UWP developers. So the first thing I'm going to do is I'm going to add a point light. So again, I'm using the compositor, which is our object factory, to create a point light. I'm setting its color to be yellow, pretty straightforward. I'm saying its coordinate space is going to be based around the dimensions of our container visual, which, as we know, is attached to our background. I then say that the point light target is going to include our background visual. So this is one of the interesting things. Lighting doesn't apply to anything unless you tell it to target it. Okay? So it's an opt-in scenario. And that's pretty useful because if you think about it, when we run our application by default, we don't add any lights. So it's all lit up and shown in full fidelity without us adding any light. If we want to add lights, then we need to do it explicitly. And I'll show you why we need to do that explicitly. So I'm going to run this now. And just by adding the light to a target means it's going to start lighting up our scene. But everything else is black. And that's because as soon as we add any lighting to a scene, all the automatic lighting is turned off. Okay? So this is now much, much too dark. It's not particularly interesting. It's actually much darker on my screen than it is up there. So I'm going to add another light, which is green, but it's essentially the same as what we did before. And if I run this, we'll have two lights, one in the top right, one in the bottom left. And we can see we're starting to get a broader lighting effect going on, but we still have some dark regions. Certainly on my screen, it's a lot brighter on your screen. And we're missing the Zune brand purple, which is what we really want to see. And in order to do that, to add a light that lights everything evenly, we add an ambient light. And so here we have create ambient light, which is part of the compositor. We specify intensity in the color purple, and again, we say it's going to target our background visual. So if we run this up, what we'll now see is we get an overall light applied to the scene, as well as our 2 point lights. And so now we can start to see purple up in the corners and so on. And so it gives us a much brighter effect, and we can see how our lighting, our colored lighting, is now a little bit more muted. Okay? So that's all well and good, but it's pretty boring. It's not really doing anything. So let's add some animation to this. So what we're going to do is we're going to create an offset animation. And what we're doing here is we start off by turning around and saying our compositor, which is, as I've mentioned many, many times, and you're going to be sick of me mentioning it, is the place we go to create all our objects. We're going to create a vector 3 keyframe animation. So vector 3 means we're going to be moving or influencing a vector 3, X, Y, and Z. And I've been in America long enough to say Z instead of Z, which is, oh, yeah, so sad. I'm going to specify that the target of my offset animation is going to be offset. Now, this target is in actual fact a string. And you'll find that there are a lot of strings in using composition, a lot of magic strings, which means if you're like me, you'll probably type offset with one F and wonder why nothing's working, and then come back to it. So that's why we can use the name of capability to pull out the string value of this property and drop that there and give us some type safety whilst we're doing it. Not all of the properties that we want to interact with are available in this syntax, so sometimes you have to type them, such as translation, but that is the key thing. We're going to insert an expression keyframe. So this is telling the animation system that this value is evaluated every frame of the animation. we happen to turn around and say that we're going to apply this at keyframe 1.0. Your animation timelines are an arbitrary duration between 0 and 1. You can actually make it between 0 and 100, 0 and 1 million, but it's easier if you turn around and say my last keyframe is 1 and do everything in between there. This .final value says, okay, whatever the final value that a property's been set to is what I want to apply to my final keyframe. And this allows us to determine at runtime what our final value is going to be, as opposed to hard coding a value. As we're going to be animating the offset of our point lights, it's going to be somewhat arbitrary where we move those to. On a full-blown application, you might have it randomized, so the lights move around your screen. And so this allows us to support that rather than hard coding a final value. So that's creating an offset animation. But that animation in and of itself isn't particularly useful unless we set values and we tell it to run. But what we're actually going to do is we're going to set up an implicit animation. And the idea here is an implicit animation gets handed off into the system, and the system monitors for a triggering event. Because our implicit animation is associated with this offset, it's going to look for changes to the offset value. If it sees a change, instead of applying that change immediately, it's going to run our implicit animation. So if our duration up here, for example, is a time span of 10 seconds, instead of turning around and saying, moving it from the top left to the bottom right immediately, it's going to animate from the top left to the bottom right over 10 seconds. And that's incredibly powerful because it means we declare what our animations should be, but we don't have to worry about it after we've declared it. And it actually allows lots of things like when you resize a grid, instead of the content just snapping to a new location, to smoothly flow. And again, I'll be demonstrating that in my later session. So this applies the implicit animation group that we've just created here to both of our point lights, point light and point light 1, point light 2. However, until we actually start changing those values, it's not going to actually do anything. So what I've done is I created a dispatch timer that runs on the UI thread that on every 10 seconds changes the offset of those lights so that they move around. Then we start it up, and I have this method, move lights, which is effectively what's going to be invoked. If we look at move lights, all it does is flip the positions of point light 1 and point light 2. Okay? So let me run this. So whilst this is compiling, just bear in mind, once every 10 seconds, the offset value of those lights gets changed. The system then just responds by moving the lights around. So hopefully you can see that. Everybody see that okay? I can switch off the ambient lighting. And so you see that they move backwards and forwards and cross each other. So you can move those however you like, and it places no load on my application UI to do this. And that is the power of composition. We've handed it over to the system. It's just sitting there monitoring it quite happily. I can resize, and my light positions will automatically change based upon the resizing. And I don't have to trigger any of this. So it really does enable a whole new generation of experiences to be built. And it will be the foundation on what the Fluent design system, which I'll speak a little bit about in my next session, is based upon to make the Windows 10 UI what it can be in terms of a competitor to what you see on iOS and everything along those lines. Okay, so that's our move lights. On the completed demo, I also showed you text moving around. So let's talk about how we can add those in. In order to do this, we're using a couple of different NuGet packages. We've already got Win2D added into our system to be able to get hold of effects. There's a guy, Rob, and I can never pronounce his last name. It's a Russian name. You guys can probably nail it for me. He's produced a NuGet package. He's actually on the Windows composition team. He's produced a NuGet package that makes it a lot easier to create text rendering using these APIs. And so that's effectively what we've got going on here. Because his is an external API, we have to pass in an instance of a compositor into his API. So he's using our current compositor. And then we can create a text surface using a string, and I've already put in your funky O for Øredev. And you can specify colors and so on and so forth. I mean, it's nothing particularly complex, but instead of using a XAML text string, such as a text block or whatever, we're actually rendering this as a surface that's cached in the graphics card. So it makes it very easy for it to animate and very powerful for it to move it around. I'll also call out the fact that we have opacity on here of 50 out of 255, so you can see the background coming through. We create a brush from the text surface. So in the graphics card memory, it renders our text according to our dimensions onto a surface. We then drop it onto a brush. We then create a sprite visual. We then drop onto our visual the brush, and we size it in accordance with the brush that was created in memory. We just, because we can, rotate it 45 degrees. You can rotate any visual, both in radians or using this property in degrees. Anchor points. So by default, the anchor is the top left. You can specify using 0.5. This is a shortcut constructor for a vector 2 that will create both values initialized to 0.5 float. So that sets it to the relative position of the middle of a visual without you having to know its dimensions. We then apply our text brush to our text visual, and we start an animation. So if we have a look at the create text animation method, this is creating just a regular vector 3 animation with a duration. We've got a keyframe that starts off by moving everything way away out of our rendering UI, offset by 2000 in both directions. Halfway through the animation, it moves it to the center of our screen. And then at the end of the animation, it moves it 2000 off the screen as well. We set our duration 10 seconds, but we can also set on animations that we're going to alternate the direction of our animation. So it's going to go out, and then it's going to come back, and it's going to go out, because we've specified that our animation iteration behavior is forever. So once again, we're declaring an animation, but it's being handed off to the system, and then the system runs it for us. So again, we have no overhead that we're having to deal with in our application. So this declares this animation, but it's back up here that we'll actually start it. So what we do is we turn around and say on our text visual, we wish to start an animation that is going to be influencing the property offset, and this is the returned animation that we're going to be running. Okay? And that's just going to sit there and run in perpetuity. And then we're going to insert it at the top of our children's stack so the text appears above our background image. So if I run this, what we'll see is we'll start off with our lights moving around, and then we have our text coming in. Now, if we were trying to do all of this with the more traditional animation systems, as our application started to become more busy, say it was processing a whole bunch of data sitting behind the scenes, these animations would start to jitter. There would be frames being skipped and so on and so forth. That's the power of this composition system. These animations are going to run 60 frames per second. They're handed off. It makes such a difference when you're really trying to create responsive applications and so on. So as you can see, our animation is going to run in perpetuity. It's moving backwards and forwards, sitting above these things. You can see lighting is moving underneath it. We can see the transparency is running through all of this. So if you think about what's going on here, it's having to compose the output by layering all of these things on top of each other, processing the opacity, processing the lighting. So it's a lot of GPU cycles is being run in order to render this, but it doesn't affect, I can move my window around. I'm not getting any jitter or judder or anything along those lines. All of those animations are still running because it's all being handed off and dealt with on the system side. Now, one thing that I will point out is that the composition team did spend a whole bunch of time evaluating all of these effects and how to process them so that it minimizes the impact on the overall system. Because if you imagine we have 50 of these apps running, then our GPU is going to start getting busy. So when it comes to the full-blown Windows 10 full creators update, running all of these new effects in the new controls, they know how to throttle it. For example, only the foreground application will be running these effects, such as the acrylic stuff that I'll be showing a little bit later as well in my session at 3:20. So that's added a whole bunch of lighting and animations. The other thing I promised to show you was how we could apply blur. And this is something that people who used Windows 7 and the aero effect really sort of missed as we moved into the Windows 8 generation. It's like, why is this UI so boring after having teased us with all this stuff in Vista and in Windows 7? And so this is really a return to form, as it were, for the Windows UI to be able to start doing a lot of this stuff. So let me just uncomment this for the time being, and let's talk through it. It's actually very similar to what we've already done for the saturation effect. Gaussian blur is just another effect. It's just another part of the effects chain. And one of the interesting things is you can actually chain the output of one effect as the input into another effect, and you can put many of these effects together to actually compose those things with blends and different compose modes and difference modes and so on. So it creates some very interesting UI, kind of like those psychedelic 70s music videos that used to throw around a lot. For the Gaussian blur, you specify your blur amount. Obviously, the larger the number, the more blurry something becomes. And the reason for that is if you're going to use a blur to put content in the background, you don't want somebody to be inadvertently trying to process and understand what's being rendered behind. You want to have a nice effect, but if you're saying putting a text or an image behind, if you make it too clear, then their brain tries to recognize what's behind it. And so that's one of the nice things about a blur effect, is it stops the brain trying to process it. It just says, oh, that's pretty, and moves on. Okay? We have different modes on how the Gaussian blur is affected. For example, on this, it says, honor the borders of the content which we're blurring, don't bleed over the edge. Because composition in reality, as it's running in the graphics card, doesn't care about the dimensions of your window. It will only worry about it if you tell it to. We're also using a balanced algorithm for blur here so that it's not as expensive, and so we can have more of these blur effects in our application. I haven't really run into a situation where the more expensive one impacts it directly, but it's there in case you want to trigger it. And then, much as the same as the saturation effect, we need to specify the source for this effect. Again, we're using Compositor to create an effect factory, which uses our blur effect definition. We create the brush. Now we're going to do something a little bit different. We're using our Compositor again, because we always use our Compositor. But we're instead going to create a backdrop brush. The backdrop brush says, take whatever is behind our current visual and use that as this value. Okay? So it's a dynamic definition of taking the region that sits behind a particular element and bringing it into the effect factory. So it's real-time changing what's behind you, which is pretty cool. There's another one, which is create host backdrop brush, and that takes what's on your desktop behind your application. Because as I mentioned before, composition in the graphics card has no concept of applications or whatever. It owns the rendering of everything. And so it can take any region on the screen and do whatever it likes with it. And so that's how you'll see in demos of Windows 10 with the acrylic material, how the desktop bleeds through is it just takes a chunk out of the background and starts to process that for you. So anyway, we're applying the backdrop, i.e. the stuff within our application that sits behind our Gaussian blur surface and passes it into our effect brush. We then set the size and offset to position it in the middle of the screen. And if we run this up, what we'll see is a blurry rectangle in the middle of our app, which is a perfect UI. We should ship it. And so, yes, you can see it. And you can see how it's real-time processing the blur as our lights move behind it, as our text scrolls backwards and forwards. Again, all handed off to the graphics card. We're not having to worry about this. It's not going to impact the responsiveness of my application. I can still have a full-blown enterprise UI sitting on top of this with data validation and so on and so forth. And I think every enterprise application should look like this, shouldn't it? So that is the key things that I wanted to show you in this demonstration. The idea was that we are bringing together a whole bunch of different capabilities of the composition system. We're using visuals. In this scenario, we just loaded an image, but we can take the backing visual of any piece of content, such as a list box or whatever, and apply exactly the same capabilities to it. You might not necessarily want to blur your list box because it might be difficult to use, but that's the real power of this system. It doesn't care where the content comes from. It can just apply these effects. It can animate, rotate, move them around, scale them, do whatever you would like to do with them. It can put them in perspective. It can push them back in Z order. Because I think where we're going with a lot of these primitives is we're now speaking the graphics card's language. And graphics cards are fundamentally mathematical machines. But they're generally used to render the 3D world, because that's a very computationally expensive system. If you think about the push towards VR, mixed reality, where Microsoft's investing an awful lot in it, many other companies are, this is a foundational system that gives you access into the graphics card to render those capabilities. And it's going to be sitting there even in your 2D applications. Right now, for example, lighting and blurring is available in your application as well as drop shadows. Drop shadows currently don't honor light positions. It's just a post-processing bitmap effect that does an offset semi-transparent dark shadow. In the future, it will honor lighting. So as you have lighting moving around, you will see the shadow move appropriately behind your surface. We're going to get to the place where all of our apps are effectively 2.5D. Like those types of games that you see, which are sideways scrolling, but you actually realize they are 3D models, and everything's interactive. That's where a lot of this facility is going to end up taking us. Does anybody have any questions about what I've shown so far? So as this is a graphics card capability, it understands when it's rendering, when the surface is actually present. So it's not actually wasting any GPU cycles because it's not on screen. The compositor understands when it is on screen, and it will start running it. So as an example, if we want to run this up, your graphics card is doing surface culling and so on, and understands when these things are off the screen. So it's not going to waste cycles actually rendering things that aren't on the screen. Because these are definitions that are being processed by the system as part of its composition cycle, again, it understands whether it's being rendered or not and doesn't actually task the GPU with processing those things. But it doesn't not understand where your text is. For example, if I bring the text on and off, it doesn't restart the animation or anything. It still processes the cycles of understanding where those elements would be. It just doesn't waste the time and effort actually rendering it out, if that makes sense. Stunned silence. Okay. Well, what I have here is a whole list of references where you can go out and learn more. Some of this from the Microsoft site. As I mentioned earlier, that Microsoft has a big push to a new design language or system that they're using as part of Windows 10. They're calling it the Fluent Design System. And what's different from many of their design languages previously is it also includes the concept of motion and the idea of a dynamic display as opposed to just static. It does evolve from what they did with what was used to be called the Metro design language in terms of not using much Chrome and so on. But to a certain extent, it starts to bring Chrome back, and it uses lighting and shadow and interaction to actually bring some of that Chrome back to give you context. And again, I'll be showing that in my next session at 3:20. If you want to look at the visual layer, there's a whole bunch of information about the visual layer and how you can interact with those things, and goes much more into detail around visuals and how you can leverage those visuals with container backgrounds and the types of properties you can manipulate on those. They have a whole set of demonstration apps out on GitHub under the Windows UI Dev Labs repository. So you can look at and see how to do some of the raw effects that I've shown here, and also how you can start pulling those into your own applications to achieve certain effects. There is also the UWP Community Toolkit that's on GitHub, and you can also download a demo app from the App Store that leverages a lot of this low-level APIs and makes it easier to consume. You can think of the UWP Community Toolkit as kind of a test bed for things that they may well bring into the framework as proper. So there are some definite accelerators there on how to use some of these capabilities. I also have a repository out on GitHub. As I mentioned before, you can see Øredev now playing. That is the repository for this application. The slide deck is in there as well. So feel free to fork that and have a look and play around with those things. And if there are no other questions, that's it. Thank you very much, everybody.